I'm worried my hair's getting messed up by wearing these headphones. And I don't know where this hair right here went. I used to have hair here. I don't know.
It's definitely the headphones.
Yeah, that's what did it. It's not my 55 years of age.
No, definitely not.
Oh, Prof, I had a quick question.
Yeah, go for it, bud.
Um, it's about the copy of like the syllabus, understanding the syllabus. Would
Hmm.
you want that to be uploaded like on the syllabus?
Yes, I think I went this weekend and set the due dates appropriately so you can do it. Let me double check just to make sure. But yeah, that's where you're supposed to turn it in week one module. It has syllabus copy and paste as an assignment. Yeah, there it is. And yeah, it says by January 26th. So yeah, I did set that one. I was worried because I found, even though I remembered setting all four of them for all four of my classes, today I've been changing test dates because evidently, even though I was confident I set them, I did not. So
Thank you.
no problem. If you already sent it to me by email, please go ahead and upload it there as well. I don't like opening things on my home computer for obvious reasons, but if I do it through Canvas, there's a little bit of protection that in case you have a virus on your computer or something like that. That's why I prefer everything sent through one as a PDF because there's a lot less viruses written for PDF than there are for Word documents and JPEGs and PNGs and all that stuff. All right. Yeah, Will, you got a question, bud?
Yes, sir. I was just letting you know I joined your class, I think on Friday of last week, and
Okay.
so I watched the Zoom lectures for the first two class periods. I
Good.
just wanted to let you know that I'm
That's
new.
cool. So, if you look in the syllabus, there's a cut and paste section at the very end. You are supposed to read that, cut and paste it into a Word document, fill it out, and make that Word document a PDF and upload it in that week one module, excuse me. So, make sure you do that. And I can give you an extension on your homework since you started late. Just when you're finished with chapter one homework, let me know and I'll adjust the points you lost since you didn't enroll until Friday.
Yes, sir. Thank you so much.
You're welcome. You might be able to get it in on time anyways. I think they're not due till tonight, but you probably aren't necessarily ready for that.
I did the first homework assignment, but I'll work on the second one. Thank
Oh,
you.
cool. No problem. All right. It looks like we've got 13 people. That's really good. Happy you guys have been able to make it. I still have, oh, it's just Will that has his hand up. It still had a little hand down there. I don't know how that hand goes away or if it's supposed to go away, but either way, it's still there. Uh, we are starting into chapter two. One thing, I did have a student at the end of my class last night, which was a 242 class, but remember I had the office hour as long as you get there by like 6:35, 6:40, you can attend the office hour on Monday, Tuesday, Wednesday, or Thursday night. And one of my 241 students came there, and they were having some problems with the the Fermi calculations or the approximation calculations. The problem ultimately turned out to be that, like, if the student had done a calculation for the number of people that fit in the Pentagon and got an answer of 3 times 10 to the sixth, the system expected you just to put the exponent 6 up there. So you're just supposed to put in the number 6, not 10 to the 6, not 3 times 10 to the 6 or anything. So if y'all are having any problems, that's a common error, and it just comes from not reading the fine print, if you will, even though it was bold print. So just keep an eye on that. Uh, Other than that, it seems like I've asked everybody questions. Just one more time, does anybody have any questions before we get started into chapter two? Okay. Uh, so chapter two starts with, and let me tell you the name of the chapter. The chapter is called Reference Frame, or excuse me, no, the chapter is called Describing Motion, Kinematics in One Dimension. So uh, this whole course can sort of be seen, the 241 course can sort of be seen as classical mechanics. And mechanics is broken up into two different parts. One part is kinematics. That's the study of motion without respect to how you make that motion happen, but with respect to if you say, for instance, I have an object that has an acceleration as a function of time, a velocity as a function of time, and initial position, you might want to know what is the initial final position at some time later, what's the final velocity at some time later, what's the acceleration at some time later. All of that could be calculated within the world of kinematics, but you can't make any sense of, for instance, how did that acceleration as a function of time, how did you get that, or how did that velocity or position as a function of time, how did you get that? That's the dynamics part, and in order to do that, at least from a classical standpoint, you need Newton's second law, Newton's first law, Newton's third law of motion. So that other part, when you actually try to address how do I make an object accelerate or have a specific velocity as a function of time, or have a specific acceleration as a function of time, or a specific position as a function of time, when you're doing that, you're actually doing the dynamics portion, and it might include the kinematics too. So that's the two parts that we're studying here. Chapter 2 and Chapter 3, we aren't doing any Newtonian physics yet. We're not doing Newton's first law, Newton's second law, Newton's third law, or Newton's law of gravity. We're just doing kinematics. And in fact, Chapter 2 is kinematics in one dimension. So that's more like you're talking about travel down a long, ideally straight road, but in principle, it could be a bead on a wire that the wire can do all sorts of curves and stuff like that, not unlike the some of the games you see in a pediatrician's office, maybe when you were a small child or something like that. You could take the bead and slide it along the wire, and it does this and all that stuff. That is one-dimensional motion, and you can recognize it as one-dimensional motion because it only needs one variable to really specify where it is. So if everybody agreed that we're going to measure the distance along the bead, along the wire from, one end of the wire, which maybe attaches to a piece of board, all the way around. If you're just measuring that distance along that wire, then, any positive motion would be some distance away from that initial spot. If you're moving in the positive direction, therefore your velocity would indicate that you're going from that one spot to the other end of the wire. If you're going in the negative direction, that would mean you're going from the other end of the wire towards the first end of the wire. That's the fact that we can indicate the position of that object on that wire with one variable, specifically the distance x, is a idea that it's a one-dimensional motion. Okay, that means we're taking out what's going to be a big part of physics in general, which is vectors. And vectors, we don't start covering them till chapter 2, but I'll be mentioning things about them right now, or excuse me, till chapter 3, but I'll be mentioning things about them throughout chapter 2 as well. So we're going to start off with the idea of motion being relative. And one of the things that I usually tell my students about that in my physics class is something that we teach in astronomy. Specifically, Buckminster Fuller suggested an idea of spaceship Earth, and what we mean by that is you really think you're sitting perfectly still. I feel like I'm sitting perfectly still, sitting on this chair, for instance, and in some sense, I am. Like I'm not moving with respect to the floor. I'm not moving with respect to the earth that's under the floor, and I'm not moving with respect to the center of the earth unless I pay close attention to directions from the center of the earth, out through the surface of the earth. And I would see, since the earth is rotating, I'm doing a little bit of motion there. But that's sort of the whole point. One thing you have to understand is if someone says a person is moving at, let's say, 50 miles per hour, that all depends on with respect to what. Generally speaking, in a physics class, if someone tells you a velocity, then you can sort of assume, if they don't tell you what it's relative to, you can assume it will be relative to the surface of the Earth. However, if it's not relative to the surface of the Earth, they've got to tell you. Like the velocity could be relative to the back of the train car, and you're in somewhere in the train car, and they're measuring it with respect to the back of the train car, or to some spot on Earth or something like that. So the motion being relative to something is an important concept. And what we mean by that in terms of Buckminster Fuller's spaceship Earth, was even though we feel like we're not moving, just as a result of the Earth rotating around its axis, at the equator, the speed is around 1,000 miles per hour. At our latitude, it might be closer to 700 miles per hour. And that's just a result of the Earth rotating around its axis. Now, in addition to that, the center of the Earth is orbiting or revolving around the sun, and that's on the order of 60,000, or actually it's more like 70,000, 67,000 miles per hour is how fast the center of the Earth is revolving around the sun. And then, in addition to that, the sun is sort of the big mass in our solar system, and it's actually orbiting around the center of our galaxy. And in that case, the velocity of our solar system is on the order of 500,000 miles per hour. It's like 514 thousand miles per hour around it. Then our galaxy, the Milky Way galaxy, is actually headed towards the Andromeda galaxy on the order of hundreds of thousands of miles per hour, and stuff like that. Then we know, for instance, within space, the individual galaxies are all getting farther and farther apart. It's not really true to say that they're moving through space as much as the space between them is growing. But the big point is, yes, everything's moving, and you can't really assume anything zero velocity. But in some cases, it acts just like it. Like I cannot sense the motion of the Earth rotating. I can't sense that 1,000 miles per hour, the 700 I'm doing here. I can't sense the 67,000 that we're moving by orbiting the sun, and I can't sense the 500,000 that we're doing as a result of the sun orbiting the center of our galaxy, or any of that kind of stuff. If I pay close attention to the stars, I can see, for instance, that it looks like there's an axis that goes right through the center of the Earth, comes right out of our North Star, and runs right through uh, a star called Polaris, which is the end of the handle of the Little Dipper. And it feels like that axis goes right through there. And then all the stars, as I look up, are rotating counterclockwise around that. That's the only reason I know that the Earth is rotating, if I hadn't studied astronomy and all that good stuff. It turns out it takes a lot of work to do that if you're trying to figure out how the Earth is moving with respect to the sun. We can, but it took the invention of a telescope, and specifically a big telescope, before we could actually do it. Because what we would do is, for instance, if we're in the month of June and we look out at a distant star and we're looking like this, and we see the star over here behind these two stars, that looks all well and good. But then when I move over here, instead of in June, but let's say in January, I look over here and I see that same star, but now it's not in front of these two stars. So that front star is tended to move left and right. That's actually called parallax. And the ancient Greeks knew about it. The ancient Greeks said if we were actually moving, then we'd expect to see the nearest stars move back and forth as we circle around something. And they said, well, there's one of two options. Either we're the center of the universe and we're moving around something, so we should be able to see the nearest things move back and forth, or we can't see that and we are the center of the universe. They just couldn't imagine the universe being so big that they couldn't detect that wobbling of the distant stars. But that's exactly what the problem was. They didn't have the technology, they didn't have the telescopes, they didn't have the sight. Even if they had the eyesight and the want to do it, they couldn't have done it because they needed a much more precise device that could zoom in and measure, over a 6 month period, exactly the relative positions of two stars in the sky. So they didn't realize the universe was that big. So they basically punted and said, okay, the universe must be small, or the universe must be centered on us, and we sort of stuck with the centered on us thing. Okay, so that's a big picture of sort of the relative motion. So with that in mind, I'm going to give you an equation that we don't necessarily cover till like chapters 3 and maybe even chapter 4. But the big thing I'm going to do here is give you a relative velocity equation. And then, because I'm doing it now, I can go ahead and give you some special relativity. And it might be the only bit of special relativity that we get to cover. So I usually do it in this chapter. Let me go ahead and start by sharing my iPad screen with you guys. So here we go. Now I'm going to share my iPad screen. That should pop up in a second. Okay. So everybody's looking at it now. So what I'm talking about far as motion relative to something else, the main thing we're talking about is we all have to have some kind of coordinate system that we're measuring our velocity with respect to. As I said, if we don't explicitly say what it's measured with respect to, you can assume it's measured with respect to the Earth. Otherwise, we have to tell you. And the way we write such a thing, if I say the velocity of Mr. Younger relative to the Earth, I could probably write that as v with a subscript m for Mr. Younger, and then a second subscript e for planet Earth. That's the way I can typically write it. And I'm going to go ahead and give you a formula for that, and it's got a kind of nice little symmetry to it that allows you to always write the right formula. So here's the formula. And I'm going to put a little arrow over top of it because it turns out this is going to be true even when we get into 2 and 3 dimensional motion where we have to deal with vectors. That being said, I'm going to show you a little bit of the relativistic results, and I'll drop the vector symbols there because that result is really just for 1 dimensional motion. But the rule is this: if I would like to know the velocity of object A, now this is one of those cases where the words that I'm saying is just as important, if not more important, than the things I'm writing. But the velocity of object A as seen by object C is equal to, now, here's the trick to make sure you get the right formula. You write V, and now the first subscript has to be the first subscript here, and then I leave a space for the second subscript. Then I put a plus, and then I write a V, and now I skip the first subscript and leave a space for the second subscript. So you see the C here, that matches the C on the left, and the A here on the left matches the A on the left side of the equal sign. Now, the big part about making all this automatically true is the two inner subscripts have to be the same. So they could be anything I want. They could be E, so I'd have VAE equals VEC, or they could be B as in boy, in which case I'd write VAB plus VBC. That is exactly right. But that's all you've got to do to make sure it's correct. You've got to make sure that this and this match this and this. And then you got to make sure that these two match. As long as you have that, then you have a correct formula. Uh, that's the relative velocity formula or the velocity addition rule. So relative
I have a
velocity. Yes.
whenever you have a second. Um, so with B, is that like object B in this formula, or what do we call B?
It could be an object. It could be another vehicle. It could be the planet Earth. It could be the planet Jupiter. I'm going to show you an example in a second, and that'll make it a little clearer. But yeah, that's
Okay.
exactly the right question you're supposed to ask.
Okay. Thank you.
No problem. So this is called the relative velocity or velocity addition formula, and it's classical, meaning it's not consistent with special relativity. I'm going to show you the special relativity version in a second. But before I do this, I need an additional rule on here, just something that comes in super, super handy. And to do that, I'm going to give you an idea. What we're going to do is imagine a road like this, and we've got one car. Let's call this car B. And we've got another car. Let's call this car A. And this one has velocity A with respect to the Earth is equal to 60 miles per hour. And this one has velocity B with respect to the Earth is also in the positive direction, but in this case, it's 70 miles per hour. So if you imagine sitting in the passenger side of car A, which would be the side that's closest to the dotted line, and you imagine instead of looking forward like you normally do in a car, you imagine it's got like one of those UPS seats that you can pull a little lever and it allows you to turn the seat sideways. You're not driving, so it's okay to do that, but you're going to imagine that so you're looking this way. Now, in order for this formula, the relative velocity formula or the addition of velocities formula, in order for that equation to be valid, everybody has to agree what direction is the positive x direction, what direction is the positive y direction, what direction is the positive z direction. In three dimensions, you have to have all three. In one dimension, you just have to have the x direction agreed upon as which direction is positive. So, to person in the passenger side of vehicle A, what they're seeing is they're looking, let's say their eyeball is looking that way. And actually, I realize now that I made it too small to draw an eyeball. But what I was imagining doing was looking that way. So you're looking that way. And what you'd say would happen is since car B is going faster than you, what you see is car B is way down there. And it starts to come up, come up, come up, and it gets next to you and then passes you, so on and so forth. So, what you start to notice is that the car B relative to you is moving in the positive direction. So, you conclude that the velocity of car B with respect to car A is positive 5 miles per hour. Now, if instead you imagine that you're on the driver's side, maybe in the back seat so you're safe, but you're on the driver's side of car B and you're watching what car A does. Now, to you, sitting this way, facing back there, what you see is the car being way out there up in front of you. And, or actually, I should say, you see the car way out that way in front of you, and it slowly comes up, comes up, comes up, comes up, slowing down, getting closer to you, getting closer to you, getting closer to you, and then it leads off that way. So in this reference frame, you say the car is actually moving in the negative direction. So, or I should say, person B does. So in this case, we'd say the other person concludes that VAB, the velocity of car A as seen by car B, is negative 5 miles per hour. Do y'all all see how that's the case? We all agreed that going to the left on this piece of paper was the positive direction. From the car A, it appears car B is going in the left direction, but from car B, it appears car A is going in the direction to the right, which is the negative direction. Does that make sense to everyone?
That makes sense. The I'm stuck on the 5 instead of it being 10.
Okay. Oh. Well, that's because you're smarter than me.
Oh, I was like, is there a formula that I don't know
No,
from
no, that's
something?
because I was thinking I wrote 65 and 70 because that's what I did in my
Oh.
class earlier today, but I did not do that. So you are absolutely 100% correct. Thank you for catching that. And yeah, I'm not using drugs or anything, I promise. So this is going to be plus 10 miles per hour. Thank you for correcting
That
me
makes
on that.
now I'm gonna, yeah.
Now it makes sense, right? And this one's negative 10. Now, this isn't a coinky dink, as they call it. This is not a coincidence. This is a real fact. So, what we just discovered is that VAB is equal to the negative of VBA. And that's a general rule. If you flip the subscripts, then you're going to reverse the sign. So, this comes with the additional rule that VIJ is equal to the negative of VJI. Okay. You might not think that's really a big deal or even remotely important, but you're going to see immediately how important it is. So with those two rules, we're now ready, even in three dimensions, to attack relative velocities. So let me show you a simple one-dimensional example to help you figure this out. So what I'm going to do is imagine that this is planet Earth, and then we're going to have spacecraft A right here, and spacecraft A is moving to the right, which I'm going to consider the positive direction, and I'm going to say the velocity of A with respect to Earth is going to be positive three-fourths of the speed of light. So I wrote three-fourths c just because I'm getting ready to do some relativity stuff too. So the speed of light's a really good unit of velocity, and it keeps me from having to write miles per hour, meters per second, or kilometers per hour, or anything like that. Now, in addition to that, I'm going to have a different spacecraft. This spacecraft is B, and it is moving this way. And the velocity of B, as seen by E, is in fact negative 7/8 the speed of light. Okay, so those are just numbers I made up. It's sort of like two cars being on the same lane headed towards each other. One's going 35, the other one's going 40. What I want to know is why do people keep calling me during my class? What I want to know is what is the velocity of B relative to A? In other words, how fast does spaceship B seem to be gaining on spaceship A? You know, if, for instance, if they're driving towards each other and one's going 35 and the other one's going 45, it's as if each of them agree that the other one's coming towards them at 75 miles per hour, right? That's part of the reason why when we design cars for safety standards, we only require them to get in a collision of 35 miles per hour with an immovable object, because that's essentially the same as if both cars were going 70 miles per hour, were identical, and ran into each other. So both of them going 35 miles per hour gives an equivalent of 70, and they design cars that way. But it's that relative motion that really matters. So in this case, we're doing one dimension, so I really didn't need to draw the arrow up there, which is a vector thing. But I want to write out and determine what the velocity of spacecraft B is with respect to spacecraft A. Notice that spacecraft A and spacecraft B both agree that the direction to the left is negative. So spacecraft A says spacecraft B is coming towards it in the negative direction. So we do expect this to be a negative velocity. Now I'm going to use my rule for the velocity addition formula, and that is VBA, which is what we're looking for, has to be equal to VB with a blank plus V with a blank followed by A. Now I look up and I realize I have VBE, so E would be a good middle subscript. And of course, once I write the E there, that means this one has to be the E. Now, I don't have a VEA, I have a VAE, but that's what the VIJ equals a negative VJI means. So I can go ahead and write this as VBE minus VAE. Now I can put in these numbers. VBE is negative 7/8 C minus VAE, which is positive 3/4 C. Of course, we need a common denominator, so I'm going to use 8. Now I get negative 7/8 C minus 6/8 C. And when you add 7 and 6, you end up getting, I just realized a mistake I made earlier in class today. You end up getting 13 over 8, because 7 and 7 would be 14, but 7 and 6 must be 13. So this is negative 13 eighths C. So if you think about that, 8 goes into 13 one time and it has 5 left over. So this would be negative 1 and then 5/8, which is 0.625. times the speed of light. And it did come out negative as we expected. So that's the way the velocity addition rule works. Let me show you another level. Let's imagine that spaceship B has a photon torpedo, and the velocity of the photon torpedo with respect to spacecraft B is negative c. Photons are the particles that represent light, so they only travel at the speed of light. And relative to B, it would travel in the negative direction and it would have a speed of b. What I would now like to know for part B, and this one was part A, by the way, part B, I would like to know what is the velocity of the photon relative to A. So now I'm going to use my same formula the way I told you before. The velocity of P as seen by A is the velocity of P as seen by something plus the velocity of something as seen by A. Well, I have PB, so I might as well put a B there, and that means I have to have a B here. Well, that happens to be the velocity that I just calculated, so we're good there. That means all I have to do is now take VPB, which is negative uh, C, and then plus VBA. VBA we just found was negative 13/8 C. So with that in mind, I can call this negative 8/8 minus 13/8, and then all of that times c because they had a common factor of c. So basically, I'm adding 8 to 13 and getting negative 21/8c. That's the velocity of the photon as seen by spacecraft A, at least classically. Just like this is the velocity of spacecraft B as seen by A. Okay. Let's take that last line out. Let's do a little further up here so I don't go right through it. So that's actually it. Now, here's the neat thing, and this is the only chance I'm going to give you any relativity unless I happen to cover the material quick enough and we can do relativity at the end of the semester. The difference between this formula in terms of relativity and this the formula in terms of classical physics is this. Instead of So this is relativistic. Instead of the formula that I have, which was VAC, notice I'm dropping the vector symbols. VAC is supposed to equal VAB plus VBC. Instead of that, I have that with the denominator of 1 plus VAB times VBC. Now, it's unfortunate that I use C as one of the subscripts because C is the speed of light, and down here I have the square of the speed of light. That's the relativistic formula. So now I'm going to repeat part A and part B using the relativistic formula. So now we'll say relativistic. And there's really only two hypotheses that really has to go, or two rules, if you will, that have to go with special relativity so that you understand what special relativity is. It just takes a lot of work or an Einstein to figure out how to make something useful out of that. But his two postulates are, one, the laws of physics are the same in all inertial reference frames. Inertial reference frame is just a way for him to say, hey, I'm going to ignore gravity here. I can't expect y'all to understand that yet, so don't worry too much about it. The other one is the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. So, if I was riding down the road at 60 miles per hour and I could throw 60 miles per hour, if I threw something in the same direction as I'm riding, then that thing would go 120 miles per hour because 60 plus 60 is 120. If, however, 60 miles per hour is the speed of light, then me moving at 60 miles per hour and then throwing the thing at 60 miles per hour would actually make someone on the side of the road see it going 60 miles per hour because the speed of light's a constant. It's a really weird concept. So let's look at how this plays out here. So here's part A. Notice I'm writing in red so it'll represent relativity. So I want to know the velocity of B as seen by A. That's going to be, as we said, VBE minus VEA. Notice I went ahead and used the trick that we can, and I'm going to say 1 minus VBE VEA over C squared. Now, this means we're going to get negative 7 8C minus 3 4 C. And then all this is going to be divided by 1 minus negative 7 eighths C times 3 fourths C over C squared. Now you can see that this C squared is going to cancel out with that C and that C. Now let's follow this out and see what we get. Negative 7 eighths minus 6 fourths. We know that that's automatically going to become negative 13 over 8c. But what is the denominator going to do? Well, the minus that you see in the parenthesis and the minus in front of it is going to make it positive, and we're going to multiply 7 eighths times 3 fourths. There's no way that I can cancel out, the 4 with any part of the 7 or the 3, and there's no way I can cancel out any part of the denominator 8 with the 7 or the 3. So I'm just going to multiply the 7 times the 3 to get 21 for my numerator, and the 8 times the 4 to get 32 for the denominator. Because of that, I know that I need to write 1 as 32 over 32. So I'm going to say 32 over 32. The two negatives make this a positive, and then I'm going to get 7 times 3 is 21, and 8 times 4 is 32. So this becomes negative 13 over 8c divided by, now you can see when I add 32 and 21, because they have common denominators, I'm going to get 53 over 32. Now, division by a fraction is the same thing as multiplication by the reciprocal. So I'm going to get negative 13 over 8. I'm going to leave the c off to the side for a second. Now I'm going to multiply this by 32 over 53. And what you can see is the 32 is 4 times 8. So that's going to cancel with the 8 in the bottom. And then 4 times 13 is going to be 52. Oh, I need that c before I do this. So the c's here now. The 32 being 8 times 4 is going to cancel with the 8, and then the 4 times 13 is going to be 52. So I get negative 52, and then the c is going to be over here. And then all I have left in the denominator is 53. So in relativity, the velocity of spacecraft B with respect to spaceship A is negative 52/53 c, which is really, really close to the speed of light. But notice it doesn't exceed the speed of light, and that's what we expect, because according to Einstein, nothing's supposed to be able to even reach the speed of light if it has any mass. And if it did, it would take an infinite amount of energy, and certainly nothing's supposed to exceed the speed of light. So the actually correct answer would not be negative 1.625 times the speed of light. It's actually going to be 52/53 of the speed of light. Now let's do part B, and part B is a little bit problematic because I can't fit it in here. So what I'm going to do is use my lasso to take this result and bring it over to the other side. So I'm going to say copy. Now I'm going to paste it over here. So we have that. So for part B, which again I'm using red now, for part B, velocity of P with respect to A is the velocity of P with respect to B plus the velocity of B with respect to A over 1 plus VPB VBA over C squared. Now, we already figured out that this is negative C plus negative 13 eighths c. Oops, wait a second, not 13 eighths c. We've got to use the right figure that we just found, which is negative 52 over 53c. So negative, oops, plus negative 52 over 53c. Now I got to divide all that by 1 plus VPB is negative c, and VBA is negative 52 over 53c. And then all that's divided by c squared. So you can see that the c squared is going to cancel out with that c and that c. And the two negatives in there are going to become positive because a negative times a negative is a positive. Now, just to make life simple, I'm going to go ahead and convert this negative c to negative 53 over 53. So it's going to be negative 53 over 53 plus negative 52 over 53. And then all that times c. So I'm just factoring out the c from the side. Now in here, I get a 1 that should be 53 over 53, and then plus 52 over 53. And lo and behold, you see that negative 53 plus negative 52 would be negative 105 over 53c, and then the bottom gives me exactly the same number, only it's positive 105 over 53, and lo and behold, you get just plain negative c, which is the velocity of the photon as seen by A. So even though the spacecraft B is traveling at 7/8 of the speed of light towards relative to Earth towards the spacecraft A that's moving at 3/4 the speed of light. The relative velocity of spacecraft B with respect to A is literally only 52 53rds of the speed of light. Then, when the spacecraft B fires something at the speed of light, lo and behold, spacecraft A still says it's coming at it at the speed of light. That's a really weird and impressive result. But the cool thing is, it happens to be correct, and that's exactly the way relativity treats things. Anybody have any questions on that? So don't worry about this. This is me exposing you to relativity, but you're not responsible for it yet, okay? You are responsible for this first part that I did right here using that equation with that. That's perfectly fine like I did here, but this relativistic stuff, I'm not testing you on that, so don't worry about it at all. It's just a chance for me to give you a little bit of taste of, the thing that I love, which is relativity. Specifically, I'm a big fan of general relativity, but special relativity is pretty awesome too. Anybody have any questions with that? Okay, so just to keep you uh, on course here, you only need to know the classical formula VAC equals VAB plus VBC with the caveat that VIJ is equal to the negative of VJI. That's all you really need for this part. And not only that, they're not going to really do much with that in chapter one, but chapter two, they're going to do quite a bit more. I remember when I covered this in trigonometry, it was things like an aircraft is flying at 700 miles per hour due north, and it's in a wind that is blowing due east at 300 miles per hour. What's the velocity of the aircraft with respect to the ground? So I remember getting bothered by that because it felt to me like I had to know something about how the forces of the wind would act on the aircraft. But that's not relevant at all, even though you could, in principle, use it to figure out the answer. You don't have to. The trick is just like as Jonna said when she was talking about movement in water. When you're an aircraft in a wind, or when you're a boat in a stream, the boat is moving in the water that's moving, and the aircraft is moving in the water that's moving. So it's that your actual thing you're flying through at 400 or 700 miles per hour is actually moving to the right at 200 miles per hour. So it's just an addition of velocities thing. So just remember that. Now, now that we've done that, I need to get more into the kinematics portion of chapter two. So, what I first have to introduce is a couple different things here. So, one thing I have to introduce is distance. Okay. If you, for instance, walk from your front porch straight down your walkway, let's say that's 50 feet. Okay. If you walk to the end of that walkway, then the distance you traveled is 50 feet. Now, if you hang a left and walk, actually, let's say it's 40 feet, and I'll draw a picture here. So here's your house, say, here's your front porch, say, and you're starting from right here, and this distance is 40 feet. And I apologize, I'm using the typical units of the British system. That's because I know I'm trying to transition you guys into using the other ones. So once I walk from here to here, I've traveled a distance of 40 feet. Now I'm going to hang a left and travel a distance of 30 feet. Okay. And I'm going to be right there. The distance I traveled is the total distance I traveled, and therefore it's 70 feet. Well, there's another concept called displacement. And displacement is can be imagined as a arrow drawn from your initial position to your final position. So I'll say displacement, and I'm going to underline it in red so you'd see that at the first leg, the displacement, which I call D1, is exactly equal to the distance. Okay, so when I walked off the front porch just to the end of the walkway, I walked a distance of 40 feet. The displacement and the distance were the same thing there. But once I took the left, then the displacement became this arrow right there. So in this case, the displacement is equal to the square root of 30 feet squared, because they're perpendicular to each other, plus 40 feet squared, which gives me, in fact, 50 feet. So the displacement is actually 50 feet, even though the distance traveled was 70 feet. Does that make sense? So displacement can be thought of as like an arrow that you draw from your initial position, and then the head is where you stopped. And obviously, during a multi-leg trip, you'll have many stopping positions. Like in this one, this is a two-leg trip. One stopping distance was D1. Another stopping distance, or excuse me, another stopping displacement was D2, which became that right there. And it's an arrow pointing, starting at where you started, and the head of the arrow is actually where you ended. Now, in one-dimensional motion, it gets even simpler, but it's still somewhat complicated. So, for instance, you could, let's again revert back to one-dimensional. Let's imagine, for instance, that you start off here and you walk, let's say 70 meters, and then you walk back. And I'm trying to draw this perfectly parallel, but I'm also trying to draw it where it doesn't cover up the other one. So now let's say I walked back a distance, and let's not put that arrow on there because I'm trying to think in terms of distance right now. Let's say I walked back 30 meters. In this case, the displacement is this. Oops. This is the displacement. And this 70 plus 30 is the distance. The displacement, on the other hand, is equal to positive 40 meters. Does everybody follow that?
If in the first example, if
Mm-hmm.
you were trying to find the displacement of the second route that was taken the 30 feet,
Mm-hmm.
is that a displacement of zero?
No, you're exactly right about that. And technically, and that's why I didn't write the D2 in there initially, you could call D1 one trip, and then you could call D2 another trip, and then this would be D total. And the displacement for D2, just for the second leg of the trip, is 30 feet upward, or 30 feet north, say, whereas D1 was 40 feet east. Does that make
Okay.
sense?
Yeah.
Okay. And in fact, that's the whole reason we use these arrows, because it turns out that when you think in terms of displacement, then you automatically start figuring out vectors, because when I add a vector that's perpendicular to another vector, I just use the Pythagorean theorem to get the hypotenuse, and then boom, I have the total displacement. Is that does that help now?
Yeah, thank you.
No problem. How about Benjamin? I didn't notice you asked a question till just now. What's your question, Benjamin, if it's not too late?
It was all the way in the beginning of the class. I had a question regarding
Sorry.
last week, Wednesday. We
Uh-huh.
didn't have a class, right? Because I didn't see the Canvas material over there on Wednesday, last
Uh,
Wednesday.
yes, we did have a class. I don't know why you didn't see it, and I have posted it. It's on my YouTube channel, so you can go there. You just look it up according to the date if you wanted to, but it should be one of the most recent things I posted.
All right, thank you, sir.
No problem. Luckily, it's all recorded, so you should be good there.
All
All
right,
right.
thanks.
You're welcome. So now remember distance. I'm going to just define them. Distance, and I'm sorry about writing in cursive. I know not everybody's learning cursive nowadays. Distance is the total distance you travel or move, and displacement is an arrow from your initial position to your final position. Okay, it's key to understand that the main reason is we're going to next define speed and velocity, and there's a slight difference between average speed and average velocity. Now, I want you to understand average speed, it has a formula associated with it, but this is not a formula you need to memorize, because this is probably a formula you already know, you just haven't thought about. For instance, when you look at your speedometer, it says MPH, and MPH means
Miles per hour.
miles per hour. Miles is a unit of distance, hours is a unit of time, and per in math and science generally means divide by. So miles per hour means you're supposed to take the miles and divide it by the hours. So average speed, which can be written S with a bar over it, that's the way we indicate average. But occasionally we also indicate it with brackets like this. So just be prepared for that. But in all cases, it's distance, like we just defined, divided by time taken. Okay? That's the average speed. There's also average velocity, which we write as normally, since this is a vector quantity, I'll talk about that in a second. You have to put an arrow over top of it, but now we're also saying it's an average, so that means you have to have an arrow with a bar over it. You can see the problem with that, it's just a pain in the butt. But the main thing is it is a displacement divided by time taken. So it looks a lot like average speed, but you see it's a little different. For starters, displacement is a arrow, so it also has this vector quantity. So I want to point out something to you. Speed starts with an S, as does the word scalar, which is what we mean when we say just a number. Okay. Whereas vector starts with a V, as does velocity. And that's because velocity is a vector. Well, it's not because of, but anyways, that allows us to remember that velocity is a vector quantity. And if you saw the movie Despicable Me, you know that the bad guy in the first Despicable Me was vector, and he said it's a mathematical term, and it means a quantity that has both magnitude and direction because I do evil with magnitude and direction or something like that, right? So it's actually correct. He was giving you a correct mathematical interpretation of what a vector is. It's a quantity that has both a magnitude and direction. So when you look at your speedometer, you are in fact getting the speed that you're traveling. It's just a scalar, it's just a number like 43 miles per hour or whatever. Whereas if you look at your speedometer and you also have a compass that tells you what direction you're going, then you look at your speedometer, it says you're going 43 miles per hour at 5 degrees east of north. Then you can say, oh, okay, my velocity is 43 miles per hour at 5 degrees east of north, and that is a vector quantity. So when you have a speedometer with a compass that measures the direction you're traveling, then you have a velociometer. Does that make sense? All right, so that's the big difference between velocity and speed, but it's a little bit different because of that displacement thing. So right now it's not that big of a deal, but if you think about some of the examples we're doing in the book, for instance, like the one I did a second ago, where I went a distance of 70 meters and then turned around and walked back 30 meters. That means I went in the positive direction 70 meters and then in the negative direction 30 meters, so that my distance was 100 meters and my displacement was 40 meters. Now, if we did that in, let's say, 4 seconds, so let's say I'm going back to this original scenario. I'm going to draw a coordinate system. This would be my y-axis, which has no meaning on anything, no relevance whatsoever, but this is my x-axis. Now, what I'm imagining doing is I am going to walk from here a distance of 1, 2, 3, 4, 5, 6, 70 meters, and then I'm going to walk back 1, 2, 3, 30 meters. Now my displacement is, is what we call delta x. So see that triangle I just drew? The triangle with the point up at the top? That's the Greek letter delta. It's the capital Greek letter delta. And you're going to run into that in physics. You're going to run into that in chemistry. You probably run into it in biology. You're going to run into it in engineering as well. And it always means change in. And that change in, unless specified otherwise, that change in always means final minus initial. So my final position right here would be x2, and my initial position would be x1. So delta x would be x2, which is 40 meters, minus x1, which is 0 meters. Therefore, we get positive 40 meters, which means I moved to the positive 40 meter in the positive x direction. Okay. Now, on the other hand, the distance traveled is 70 meters plus 30 meters equals 100 meters. And I can follow this up by writing up here on the average velocity thing. That's going to be delta x with a vector symbol over it over delta t. Whereas the speed is going to be distance over delta t, or you could just say distance over time, but I wanted to show you that the delta t sort of means the same thing. So for this particular trip, if it took 4.0 seconds, what are V bar and S bar? Okay, in other words, what's the average velocity? What's the average speed? Well, solution, the average speed is equal to the distance divided by delta t. That's going to give me 100 meters divided by 4.0 seconds, which equals 25 meters per second. Okay. Now, this is all one-dimensional motion, so it doesn't have that weird thing where I went 40 and then I went 30, so the net result is only 50. It's not that, but it did do something weird. Now you can see that the average velocity, which is delta x over delta t, is going to be 40 meters divided by 4.0 seconds. So the average velocity, in fact, is only 10 meters per second. That's the big difference. Velocity on average is displacement divided by time. And that literally means just subtract the x value in one dimension, subtract from the final x value the initial x value, and then divide that by the time taken. That's your average velocity, at least in one dimension. And your average speed is the distance you traveled divided by the time taken. And you can see that those numbers came out quite a bit different. Anybody have any questions on that? Okay, so that's how we handle average velocity and average speed. Let's look at example 2.1. So I'm using the book here, and I will read these examples. But it's probably good if you have your electronic version over in case you miss something. But I'm going to read it. It says the position of a runner is plotted as moving along the x-axis of a coordinate system. During a 3.00 second interval, the runner's position changes from x1 equals 50.0 meters to x2 equals 30.5 meters as shown in figure 2-7. What is the runner's average velocity? So what they gave us was the position of a runner is plotted as moving along the x-axis of a coordinate system during a 3.00 second time interval. So a big part of physics initially is just learning what the symbols are to represent certain quantities. So a time interval of 3.00 seconds is what we've been representing as delta t. Okay. The runner's position changes from x1 equals 50.0 meters to x2 equals 30.5 meters. What is the runner's average velocity? So that's what we're looking for. Now, as I was telling you, a big part of physics when you first start is learning certain symbols mean certain quantities, and then there's formulas that relate all these symbols to each other. And a good fraction of your physics problems can be answered almost blindly just by finding a formula that has the symbols that you have plus the symbol that you want to solve for. And you just plug them all in there and solve for the symbol that you want. Okay. 9 times out of 10, and I'm just making that stat up out of thin air with no real meaning behind it, but 9 times out of 10, that's going to get you the right answer. As you progress in physics, you'll learn there's little nuances. So sometimes numbers you might think are positive or negative. Sometimes your subtraction, you have to subtract, all sorts of weird stuff like that. Over time, you'll learn how that works. But initially, at least as a first try, plug in your equations and see if they work. If you have no idea of how to do it otherwise, what's going to harm? What's it going to harm? Okay. So with this in mind, what I know is solution. The formula we have is V bar is equal to delta X over delta T. And as I said, unless we explicitly tell you otherwise, delta means change in, and change in means final minus initial. The final was X2, and the initial was X1, and then the delta T is 3.00 seconds. The X2 was 50.0 meters, and the X2 was 30.5 meters, and the X1 was 50.0 meters divided by 3.00 seconds. That gives me V bar is equal to negative 19.5 meters divided by 3.00 seconds. Now, 3 goes into 18 6 times, and then I got 1.5 left over. So that's 0.5 times 3 gives me 1.5. So I'm going to say that the actual answer is 6.5. So I get negative 6.50 meters per second is the actual velocity. Notice the fact that it has a negative. That means the velocity is such that you're going from a small x to a large x, and therefore you're moving, or excuse me, yeah, from a small x, or excuse me, from a big X to a small x, and therefore you're moving in the negative direction. That's why the symbol's negative, and that's why that's part of the vector quantity. Your a scalar speed should never give you a negative answer. Okay, because it's a distance which can't be negative divided by a time which can't be negative. Whereas the velocity, you're not actually given a negative magnitude. Your magnitude is 6.50, but the direction is in the negative direction, so you stick a negative sign on it. Anybody have any questions for that one?
For the items that are scalar, is that
Mm-hmm.
right? It'd be like distance. Can you have negative time?
No, you generally don't have a negative time. You could sort of think like if you started timing projectile at the second it reached, some arbitrary height, then you could say 3 seconds earlier is when it left the cannon. In that case, you could sort of point as that as a time of negative 3 seconds. So in that sense, you could use a negative time, but generally speaking, magnitudes of vectors, which we'll learn in chapter 3, are never negative. So in that sense, you don't really ever have a negative scalar speed. You might have a some idea of what you might call a change in time being negative because you're going back in time, but you're never going to have a negative speed.
Okay.
Okay, good question. All right, let's go to example 2.2.
Rob, do you know what page number we're on?
Yes, we're on page 24. And actually, it's starting 25 because the 24 is at the top of example 2.2, which means the end of the page is 24. And therefore, this is probably on 25. So, example 2.2 says, how far can a cyclist travel in 2.5 hours along a straight road if her average velocity is 18 kilometers per hour? Now, since they said the road was nice and straight, you don't have to think about distance versus displacement being different because she's going in some sense a fixed average velocity for 2.5 hours, and we're trying to figure out how far she can get. And in that case, we're really thinking about what's the most she could do. And if we wanted to know what the most she could do, we're not thinking about her turning around at any point. That would be pointless. So what we have here is a cyclist can travel how far can a cyclist travel in 2.5 hours? That means delta t is equal to 2.5 hours. Along a long straight road, if her average velocity is 18 kilometers per hour, our symbol for average velocity is v with a bar over it, and it's 18 kilometers per hour. Now, we talked about chapter 1, we talked about the base units for the SI system, and those are the MKS system. So it's meters for length, it's seconds for time, and it's kilograms for mass. That means your velocity must be in meters per second, your acceleration must be in meters per second. And you always know that when you're using those units, these equations work. But there's a lot of times where you can use units that aren't your base units. You just have to analyze what the units are doing in the formula. And if they all work out, then that's great. If they don't, then you have to either reduce them to the base units or make the units similar. So, what I'm going to do here is show you how you can actually keep the units that we have without converting them to the base units of meters per second. What we have is the average velocity is equal to delta x over delta t. And in this case, if I plug all this stuff in here, what they're asking for is delta x because they said, how far can a cyclist travel? And by asking how far, you're really thinking of a maximum amount. So you're not thinking derivatives and all that stuff here because, taking a derivative sitting equals zero gives you a maximum. No, in this case, you're just thinking the bike is not going to turn around or do any stupid crap like, come to a stop, wait a little while. No, she's going to try to travel continuously at an average speed of 18 kilometers per hour. So now I'm going to plug these numbers in this formula. And sometimes it's smart to actually solve the formula for the variable that you want before you actually plug the numbers in. I notice students don't do that. It's a good thing to do. I highly recommend it. But a lot of times they just put the numbers in. So I'll try to work them more like that occasionally, but I'll also do it more where you solve for the variables first. In this case, I'm going to plug the numbers in so we can make sense of the units and see if they're going to work. So the average velocity is 18 kilometers per hour. Remember, I told you the 18 and the kilometers per hour are being multiplied by each other. So that helps us know what we can do with units. That's got to equal delta x, which is what we're solving for, over 2.5 hours. Okay. Now, the fact that the velocity's in kilometers per hour and the time's in hour is what tells me immediately that will be fine. We can use these units. What you can do to think about that is you can make this into a proportion. Specifically, you can say 18 kilometers over 1 hour is equal to delta x over 2.5 hours. And then you know to solve this equation, you multiply both sides by 2.5 hours like this. And when you do this, you can see what happens. The 2.5 hours being multiplied by 18 kilometers per hour forces the hour here to cancel out with the hour here. And on the other side, the whole 2.5 hours cancels out with the whole 2.5 hours. So what we ultimately get is 18 times 2.5, 18 times 2. 18 times 2 is 36. 18 times 0.5 is 9. So I get 45. So 45 kilometers is equal to delta x. And that's the actual answer. She can travel a total distance of 45 kilometers, and that's it. So that's how I was able to look at the equation and see whether the hours worked out. I mean, whether the units worked out. If it hadn't, like if they'd given me a time in minutes, then I'd either need to convert that minutes to hours or convert the 18 kilometers per hour to 18 kilometers per minute, or I could basically convert it to meters per second and then convert the time to second, and that would work as well. Okay, so don't always feel like you have to, but know that if there's any doubt, you can always convert all your units to the base system, and then every equation will work unless it explicitly says otherwise. And I can't remember the last time I've ever had an equation that was made up with very specific units other than in lab, like when we do magnetic deflection in 242. Anybody have any questions on that? All right. Got about 5 minutes left. I'm going to do example 2-3 now. And example 2-3 says, car changes speed. A car travels at a constant 50 kilometers per hour for 100 kilometers. It then speeds up to 100 kilometers per hour and is driven another 100 kilometers. What is the car's average speed for the 200-kilometer trip? So what I'm going to do here is I'm going to say V1. Actually, I should say they're asking the speed. So it's probably best to call this, instead of a velocity, to call it a speed, because we really don't have any idea of what direction it's going or anything like that. So speed is probably more appropriate. So I'm going to say speed 1 is equal to 50 kilometers per hour, and it does that for, or she or he does that, or the car does that for 100 kilometers, which I'm going to assume the 50 is 2 sig figs and the 100 is 3 sig figs. Then S2 is 100 kilometers per hour, and they do that also for 100 kilometers. Now you look at this, you say, well, they did 100 kilometers per hour for 100 kilometers, and they did 50 kilometers per hour for 100 kilometers. It seems to me like the average speed should just be 75, because the average of 50 and 100 is 75. But that's the difference between everyday life and science, where you have very specific definitions of things. What they're asking for here is, what is the average speed? And the equation we have for average speed is the average speed is equal to distance traveled divided by time taken. So we know the total distance traveled is 200 kilometers. But the time taken is something that's quite a bit different. So we have to figure out that. We know that speed is equal to distance divided by time. You could write that as d over t or d over delta t. In fact, I often write it d over t. So with that in mind, you can solve for t. For instance, S is equal to D over T implies T is equal to D over S. So T1 would equal D1 divided by S1. D1 is 100 kilometers and S1 is 50 kilometers per hour. Again, you can see that the units, because we're dividing by a fraction, that's the same thing as multiplying by the reciprocal. So the hour will come up top and the kilometer will go to the bottom. So those kilometers are dropping out, and we get, in fact, a answer of 2.0 hours. Similarly, T2 is equal to D2 over S2, but D2 is also 100 kilometers. However, S2 is 100 kilometers per hour. So again, the kilometers cancel out and we're just left with hours. But in this case, it becomes 1.0 hours. So now we know the total time is 3.0 hours. So we can take this and stick it in here. And 200 divided by 3 is 66.7, or 67 if we only use two sig figs. So this is 67 kilometers per hour is the average speed. Any questions on that? All right, now that's actually all I had planned to do for tonight, just to keep it on track with my online class, with my face-to-face class. Next time, I'm going to be doing something where I take some of the stuff we discovered. I'm going to figure out, for instance, that how the difference in average velocity and average speed, how that translates to an instantaneous velocity, and then later to an instantaneous acceleration. It turns out all you have to do is measure the change in distance divided by the change in time for the average speed to get the instantaneous speed. You just make the time interval get smaller and smaller and smaller so that the ratio is always the same quantity, no matter how small of a time you use or how big of a time you use, up to some limit. So if you get that ratio being the same number for each time interval you use, then you know you've used a small enough time interval. That would give you your average speed, and that's how your car calculates, or excuse me, that would give you your instantaneous speed, and that's how your car calculates your speed that it shows on your speedometer. Velocity is the same way. You're going to allow the time interval to get smaller and smaller and smaller. And in addition to having a magnitude, which is the, how fast it is, you're also going to have a direction. That's the main thing. So we can say that V instantaneous is equal to the limit as delta t approaches 0 of delta x over delta t. And of course, we recognize that from calculus is dx over dt. Similarly, you might find that the average acceleration is delta v over delta t, and that would suggest that the instantaneous acceleration would be the limit as delta t approaches 0 of delta v over delta t, which we recognize from calculus is dv dt. So that's the stuff we're going to start with next time, and from that I'm going to derive the kinematic equations, and that's a very important thing because that's the type of problem you should be able to do as a calculus-based physics student. Make sure you chat me your first and last name if you haven't already. Everybody's free to go. I now am starting the office hour, but since we got a couple minutes, anybody that's in here for 241, if you have any questions, you'll get the first dibs, but from there on out, anybody else can ask questions as well. So anyone have any questions?
Yeah, I have a question, Professor.
Yes,
I
sir,
was
Benjamin.
reading, yeah, I was reading the syllabus. It was saying like a face-to-face test. Does that mean that we have to come to the campus to take the exam?
In general, that is an option. I mean, you're allowed to come to campus and that will be free. but you do have to have a proctored test. So I offer a specific time every face-to-face test where you can come and do it in my class, but that would be on campus. And the all the TCC campuses have testing centers, and each testing center has one night a week that they work. So you could, in principle, go to one of those, whichever one's closest to you. But in addition to that, there's other resources. Like if you're, for instance, 3 states away, you might find a local college or a local school or teacher or principal that would be willing to proctor a test for you. But there's ways we can do it other than you have to actually come to campus.
Okay, so other than that, that being optional, that means all our tests and the final exam is the lockdown browser, right? Am I correct?
You would definitely need the lockdown browser if you're doing this online.
Okay,
And we might even use Respondus Monitor, which is means you have to have a camera. So if you are wanting to do a face-to-face test somehow online, you're definitely going to need a camera. It maybe like some people can do it with using their phone, using Zoom, and then you could use the camera on your phone to film you while you take the test on your computer in your room, and I
okay,
could watch you or someone else could watch you through that camera.
okay, got you.
Okay,
All
so
right,
there's a lot of
thank you.
different ways. We just have to, work out some things to make sure. Like normally, I make you show me the whole room. You have to close the door, and then the door needs to stay closed. You have to keep the speaker on the whole time so I can hear if anybody's talking to you. At any time, I can ask you stop, show me everything around the room, and all that kind of stuff. But just some kind of measures to make sure there's no one else in the room helping you or anything like that.
All right, got you. All
All
right,
right,
thank you.
no problem, Benjamin.
All right.
Anybody else? Anybody else have any
I have a
questions?
question.
Go for it. Yes.
It's more about the lab one that's due tomorrow. Can you hear
Hmm.
me?
Yes.
Is it okay if I ask a question about the lab?
Yes.
So I have a couple. So we weren't assigned partners, right? So this is just a single lab that
Yeah,
was
exactly.
okay.
Unless you happen to know somebody in class you want to be a partner with, you're not going to have any partners.
Nah, I went through it and then I finished it, most of it, and then I forgot to ask if there was partners, but it's fine if there's no one.
Yeah.
Uh I also had a question. I was using my fiance's iPad to just show all my work and type on an actual document. Is it okay if
Hmm.
I just send that in?
It has to be in a PDF format, so you
So
can
I can
take.
convert it to a PDF and
Yeah,
it
that would
shows
be
all
fine
the
as well. Yep.
okay. So if I
But
can
remember,
just
you've still got to turn in the actual write-up of the lab because I need the write-up of the lab with fonts other than black so I can see exactly what you entered it with. Not the addendum, but the actual write-up of the lab. That's supposed to be turned in. But any of the calculations you did, you can just take a screenshot of it from the iPad and then paste it into the Word document that I gave you and then make that a PDF. If it doesn't come in as the original document, you're going to lose significant points.
is it okay if I just turn on my camera and show you what I'm talking about?
Yeah. Let me.
Can you
There's
see
a
me?
way I can set it up where you guys can share your screen.
Can you
Okay,
see
so
me?
now you can share your screen. Oh yeah, I see you.
So
You
this
can share
is
the screen with me if you'd like.
I don't know if it's on my I or her iPad. It's
Gotcha.
like I have the document for the lab pulled up
Okay,
and I'm
right.
just writing on top of the document.
Oh, then that's great. Yeah, that's
So
no
I can
problem.
just do
Because
that because I can convert it straight into a PDF.
yeah, that's good, and it's handwritten, so it's not even that important that it be a different color font because handwriting I can tell clearly something
Oh,
you
okay.
entered.
And that's
So
why, okay, so if it was like text, so it'd have to be different color.
yeah, if you typed it in, I would need you to make it a different color.
I just made it all red just to be safe.
That's cool. Thanks, Nestor.
Okay. So that's the only document that needs to be turned in, right, for the lab?
Yeah,
Just that form?
well, any kind of thing, any kind of data or whatever, that has to be in it right where it's supposed to be. But like if you made graphs, they would have to
Yeah.
be in it.
Okay.
But yeah, that's all you got to turn in.
I got one more.
Okay.
So I this is probably a dumb question, but for boxes or data tables, since there's a units on the like say circumference that has parentheses centimeters,
Hmm.
you don't want us to put units inside the numbers inside the box, right?
when
because
you're showing, yeah, if it's got parentheses like next to a row or a column,
yeah.
then that stands for all of it below, so you don't
Okay.
have to put it in there. But if you didn't, you need to put it with each little one. That's why it's better to just put it in parentheses at the top of the
Okay.
column or the left-hand
Just
side of the
making
row.
sure if you were gonna like catch on every little single detail if
I
you
would
missed that.
normally catch that as 5 points if you didn't have that centimeters in parentheses and you didn't put any numbers with it. I'd say no units -5. So yeah,
Yeah,
you
but
did
since
right.
it's already has it in the document, it's should be all good then.
Exactly. Yep.
10-4. Hey, I appreciate it, man. You have a
No
nice night.
problem. Have a good one, Nestor. Anybody else have any questions? I'm here all night, guys and ladies. Actually, the phrase guys for me is non-gendered. So
I just want to say thank you.
no problem, John. Have a good one. Ryan, did you have anything? All right. Well, I think, and I don't see any chat coming off, so Ryan might not even be here anymore or might not have sound. So I'm giving him this couple of seconds. Otherwise, y'all have a good one. Thank you for coming, everybody. Have a good day. Oh, for you guys, your lab, I'm going to still meet at 11 tomorrow. If y'all can make it, you're welcome to, but don't worry about it. You're not required. But I'll be covering that tomorrow. Have a good day. Bye bye.